initially in the morning, we hear a lot about the potential for the seismic application, and obviously seismic is going to come and go because the earthquakes are unpredictable. It's going to take place, and it's going to have structural damage, and we will definitely continue to invest. So if I take the deployment of tall wind turbine towers, my question is there any market? So I'm going to spend quite a bit of time on the market sector. So if you were to develop a technology, where you want to develop a technology so that there's a market available, and then work towards what are the benefits on using hybrid simulation in this particular class of problems. How many of you think that wind energy is great? Okay, several. So how many think it's not a good idea? It's a nuisance, it makes noise, it's ugly. I've heard all of that stuff. If you're in that category, you can leave now because I'm going to be talking mostly about the future of wind power. So for some reason, I got into this topic because Iowa produces a lot of wind energy, and so I structured my talk primarily about, the motivation behind what I am proposing here, the potential solution to some of the upcoming wind power production, and new technologies, and how do we validate them, and that's where the hybrid testing is going to come in. So for those who are not familiar with wind power production, this is the wind installation in the U.S. Today, pretty much. So we have about 89 gigawatts of wind power production, installed wind power production in the U.S. The largest installation is in Texas. The second largest is, I was going to say Iowa, but Oklahoma just beat us with almost about 150 megawatts. California used to be number 2, but they are pretty in the low level right now compared to other states. One thing to realize is there's a big area here. So there are all of the white area, the southeast basically tells you that there's no wind production right now. And if you look at all of the red dots, that's where the wind manufacturing facilities are. It could be turbine, it could be the towers, it could be blades. So you could see there is a lot of companies positions in the southeast, even though production right now is almost zero. So why are we not producing? So this is the map of 80 meters, at an 80-meter altitude, the wind power, the wind speeds. And you could see that comes from the fact that we have good wind conditions in the interior of the U.S. So that's why we are producing a lot of the wind in Iowa. Minnesota is definitely doing, and then you can see Oklahoma going down to Texas. We are doing pretty good. The slide on the right shows how the wind power cost has gone down. So we have different lines. The blue line is basically in the interior region. You could see the prices have, over time, has come down quite a bit. The higher prices are in the areas outside of the interior, where the cost of energy is, wind energy is relatively more expensive. But the cost of wind power production has come down pretty significantly. I think we are right now, if I compare to the cost of wind energy in the 90s, we are only paying 10% of the cost that we paid in the 90s. So it's a big reduction to the cost. So the commonly used, so my focus here is on the tower itself. Some of this discussion applies to blades, as well as the questions asked earlier about the blade dynamics. So this is what we do. We typically build them at an 80-meter hub height. They are manufactured steel tubes, a very well-established market. But with the 80-meter tall hub heights, we typically would have 3 steel tubular cells stacked on top of each other, and that would help us to reach the 80-meter hub height and then produce wind power. So that has been the past. My interest is going taller. So why do we want to go taller? Because we can increase the production by going taller, and we can reduce the cost of wind energy further. So federal government has provided production tax credit to the wind industry up until now, and that's going to be phased out by the end of 2019. So in order for this market to survive, you still need to reduce the cost of wind power. So how can you reduce the cost of wind power? One option is to make the production more with the same system. That's going to help us reduce the cost. How do we increase the production? We can go taller, get into a steadier wind condition, and that would actually help us reduce the cost of energy. If we can design towers and blades with the hybrid simulation techniques that by understanding their dynamics, we can actually reduce the cost of installation cost of the system. So that can also reduce the cost. By going taller, you will see that we can do a more market penetration with the wind power, and then the taller towers also provide other benefits which I'm not going to go into. So if you look at the growth over time, you could see in the 90s we built turbines that's capacity is about 50 kilowatts. Today we built typically with the 2 megawatt capacity. The companies who do business in the U.S. or sell wind turbine systems are starting to sell 3 megawatt. Offshore has installed up to 6.5 megawatt overseas, and there are designs available to go up to 9 megawatt for just one machine. The benefit is, as you can see here, if you just take how many houses you can power with this one, you will look at how much can we increase in terms of the wind power. So as we continue to grow, so this is where I included some cost information. So I think 10% of the cost in the 80s and 60% of the cost in 2010. The orange line tells you the cost of wind power over time. So we are pretty much reducing the cost of wind power. And as I said, we will not be able to survive unless you bring in new reduction to the cost. So you could see that with time, what we are doing is we are going taller, we're getting bigger in terms of the rotor diameter. The nameplate capacity of the machine itself is getting bigger as well. So that's where the benefits come in, and that actually will help us reduce the cost of wind power over time. So in the 2010, we were doing 80-meter tall hub height. We're supposed to be doing 100-meter within 3 years or so. We are starting to do 90, 95 now. 125 was projected for the future, and then even going to 150 meters. Germany still has a pretty good incentive, and they promote wind power or renewable wind power for a lot of reasons. And they actually have gone to, I think the tallest wind turbine system in the US, in the world is in Germany, and the height is 176 meters to the hub. So that's more than twice what we are building in the US. So if you look at what's happening to the market, you can see the top circle is basically the rotor diameter, so that's slowly creeping up to 110 meters, and I think Siemens has a rotor now goes to 120 meters for the U.S. market. You could see the nameplate, which is the bar chart, which says that you started at 600, 700 kilowatt. Now we are up to 2+ megawatt. The red line is the tower height. You can see that's stalled at 80 meters. So what is that stalling the tower height? It's basically the technology that we are using, contributing to that effort. So let's take a look at what was projected over time again, and by 2020, we are supposed to have 5 megawatt machines with at least a 125-meter rotor diameter, and there are proposals to go up to 150-meter plus in terms of tower height. And this is what the market is expecting to happen. I also talked about the fact that there will be a market penetration taking place if you can actually increase the tower height. So the blue region, the dark blue region tells you where the strong wind is at 80-meter hub height. If you can go to 140 meters, so we're going to increase the height by 75%, that's what's going to look like. So remember I said the Southeast has a zero potential for wind power today. That's all based on 80-meter hub height and the potential implications of that wind power production. Now, if you go to 140 meters, the conclusion is that you can actually produce wind power in every state in the U.S. And that's what the DOE likes to see that we do. So why 80-meter hub height? So this is the problem. So we came up with the technology and that's constrained by the transportation. So if you go taller, your base gets bigger, and then you cannot transport them. So solution, you can segment them and transport them, and if you do that, the cost of construction goes up pretty significantly. The maintenance becomes an issue, so you can't quite do that. So there are newer technology being introduced, and one of the technologies that I've introduced is known as the Hexcrete tower technology. It's actually based on concrete concept. So this effort was funded by the Department of Energy. The goal is to get rid of the transportation challenge. So the concept that we came up with is basically that introduces the tower using prefabricated modules of concrete segments of high strength or ultra high strength, so that we will be able to reduce the weight of the system. And what we will be transporting to the site is basically columns and panels, and we will cut them to the length what the owner wants to transport. So if transportation is an issue, we can cut it shorter. If not, it can be longer pieces. And on site, we will assemble these cells. And these cells are made such a way that the precast fabrication can be done fairly easily without requiring any special formwork. So we use hexagonal shaped columns and flat panels, and then create a post-tension cells here, and then stack them and create a Hexcrete tower. So that from a design point of view, in the construction and transportation, we don't have any challenges. We can go as high as we want. And the DOE asked us to come up with the height for the project, and I ended up recommending that we do 120 meters and 150 meter, 40 meter design, because I think if you cross 140 or 150 meters, especially 150 meters, we don't have cranes in the U.S. that can reach up to the top. So we have to stop it at some point. So right now, my vision is that we could actually go up to 140 meters and build these systems. And we're doing market analysis to show if you go to 140 meters, what will be the impact in the interior, what will be the impact on the southeast. And so if anybody is interested in the technology, if you Google, you will see a lot more information. So with the Hexcrete development, so the challenge is we don't know how to make this. So one of the concerns that from the industry is that, okay, it's all great, sounds great, you got pieces coming in, and you're putting them together with some cables. Are they going to stay together during production? Fatigue problem? These are the questions came up. They're fair questions because the wind turbines actually fail more frequently than maybe bridges fail. We don't hear about them because they are typically, they don't advertise the news. But they do experience failure, and therefore the concerns is still there in terms of can they actually sustain the load. So if you look at the technological challenges, so it could be Hexcrete, it could be something new, basically the system is going to get more and more complex, and you will see that in the remainder of my presentation. The loads on towers are not readily available, so companies don't share what loads they typically use for design, and they don't necessarily collect them during the actual operation. So everything is based on simulation. It's actually based on a fixed model CFD analysis, which is not very accurate. The data protected, the loads depends on many factors: wind speed, the rotor speed, pitch control. So the actual machine has become more sophisticated, so that kind of influences what loads the system actually experiences. So as I said, for towers, and the same applies to blade, what they do is they build a solid model, so you have a stiff tower, then they push the wind through the towers using CFD and figure out what loads are being simulated. And we argue that that's not necessarily an accurate approach to do it. And then these companies rarely provide any validation or feasibility study in terms of why the system can work. So with the Hexcrete development, what we did was we actually did go through a series of exercises to show that we have computer capabilities now. If it works, QuickTime is not available. I'll try this, maybe the same case. That's okay. Yeah, I'll show you the videos later if time permits. But these are coupled, fully coupled analysis between the system and the wind surrounding it. What we found was the loads on the towers and blades are actually lower than what companies normally simulate. So obviously what they're producing is maybe safer design, but it's a more costly design. What we found was the loads can be reduced because with the fully coupled analysis, you can see, I think this won't work either. So with the fully coupled analysis, you have the same issue that you have a stiffer system. This analysis, we were able to look at not only the wind effects on the towers and the rotor, but after that wind energy is being, wind is being taken, the energy being taken away, it creates a turbulence that affects the tower behind it, and what would be the impact of that turbulence on the adjacent system. So for the Hexcrete development, I've been fortunate enough to find funding to do different components. So first we actually did component tests to show the connections between columns and panel can work. We looked at different types of connections. I know this is, some of you may not be interested, but the point I want to make is that we looked at different ways of connecting it so we can give them multiple solutions. Then what we did was once we connected it, we identified in the whole tower which panel is going to be the most loaded panel. So depending on the height, because we taper the tower, then we apply the load to show the connection can survive. It's a very brute force approach where you only take one set of load and apply. So there's situations like that, hybrid simulation can be a very powerful tool if you want to use it. Then when we received the DOE funding, we had industry partners and we were able to design different systems. And in this case, we identify a segment up here, which we thought is the most critical. And then we were able to do the actual design. So this work was done in collaboration with Siemens using one of the turbine, which is the 2.3 megawatt. And then we decided that we will actually do a test to show the whole thing can actually work. So here's the construction right here at the Mass Lab. This is the testing, the instrumentation. So here we had to come up with, because we didn't have the hybrid simulation capabilities, so we have to come up with how we would load the system, and we chose multiple directions load and came up with somewhat of a complex load protocol. You can see at the bottom of the table here that we came up with the different load combinations, but we were guessing in terms of loading the system more effectively. So it's not that something I wish we had a fluid structure interaction model that provided information so that we can actually apply the load more like what the system will experience. So here's a test of the system here, which hopefully will work. Oh, it's also say quick time. So this test was done here in the lab. Basically, we came up with the load protocol to make sure that we are covering the envelope load rather than doing a hybrid simulation type testing. So the improvement that I could think back in terms of what I would have done differently is that I could have included variation in wind speed if I could. I think the hybrid simulation can do that. Account for the effects of fully coupled fluid structure interaction, so the loads on the tower would be more realistic. And then we could also look at modeling the effects of pitch control and starting and stopping the turbine that puts in an additional load to the system, and then even vortex effects if needed. So why would we do more tests? If the industry is doing pretty good, do we really need to do more tests? And I have a Hexcrete technology that has been tested. In fact, you will find there are more and more new technologies are coming along. And the offshore market is starting to grow in the U.S. So we now have the first offshore energy production installed in the U.S. And there's a projection that we will have about 25% of our wind power actually being offshore wind power production. And I'll give you some ideas there. The tower vibration is going to continue to increase, so that needs to be accounted for in the actual testing. The cost reduction I mentioned is possible, so by designing towers with a longer lifespan will also help us reduce the cost. I think we can help establish realistic loads on various wind turbine tower technologies and confirm feasibility of tall towers. So here are some examples of, so there are two other companies. The one on the left is the guide wire tower concept. The tower itself is skinnier than what you would expect. This goes up to 120 meters. It's designed by Vestas. The one on the right is by a company in Spain called Nebra Wind, and they are doing a hybrid concept with the lattice system, and they are designing to go up to 140, 160 meters. Offshore, as I said, this is the Block Island wind power production, and our goal eventually is to go towards floating wind turbines for the offshore market. So the offshore is going to have floating systems, and that's going to require pretty significant testing to make sure these systems can accommodate large loads. So when you do tower designs, we typically keep away from what's known as the 1P, 3P frequencies, where the passing blade frequencies cannot, therefore, resonate the tower frequencies. So we keep them in 3 different areas. So one is known as a soft, the other one is soft, stiff, and stiff. Most of the towers are designed to be soft, stiff. So including the hex rate, we keep them between the 1P and 3P so that we can relatively have a stiffer system. There are companies pushing for what's known as a soft system, so they could cut down the amount of material they use, but the tower will be very flexible and scary. That's what happened. So I don't think this video will work either then. So these are soft towers. There are a couple of them have been installed, and you will actually see them. Unfortunately, the video is not working, but these towers basically wiggle when the wind blows, but when the production is not there. But how do you make sure that this system can survive? In fact, they put up few towers. One has already crashed. So there are concerns. So these are the type of system where we can actually use testing more effectively. So with my time getting closer, so the question is, are we really going to have a lot of wind power production coming up so that this is a worthwhile investment? So if you look at this graph, you can see the different color graphs. So back in 2000, this is what projected for wind power production worldwide, the light blue or cyan color. Then they changed the graph and said, oh, no, we're going to do better than that. Then they changed it to purple, then they changed it to blue. So the growth in wind power is going to be there, whether you like it or not. You can be a strong supporter or you can oppose it, but I'm saying where the market is going. It is going to grow, and the U.S. projection is going to be that we're going to quadruple the installed capacity from where we are. The white line is basically what we are doing over time. So you can see that we are staying on, basically the curve is being adjusted based on what the market is doing. This is a projected wind power for the U.S. So you could see that typically each year, we actually install more wind energy than any other source of electricity in the U.S. now. So the yellow band tells you how much installation is expected to take place over time. So our goal is by 2050, we want to be able to produce 35% of our electricity from wind. That's huge. So I think Khalid mentioned 28% for Denmark. In fact, their numbers have gone up to 48% today. Iowa, last year, we produced 37% of our electricity from wind. I think Minnesota probably in the 13, 14%, I think, at the most. Nationally, we are doing 6%. So from 6%, our goal is to go to 35%. So the growth will take place because that's where the significant investment is going. And another thing to note is that wind power is today the largest source of renewable power in the U.S. So it used to be hydropower. Up until recently, wind power has taken over in terms of installed capacity. In fact, the hydropower guys are getting together to figure out how do we come back as the #1 source, because the wind can be installed in many places easily. So why, so the usefulness or effectiveness of hybrid simulation. So if you can bring in hybrid simulation to this particular field, you can actually make an impact because the system, in this case, remains elastic. So doing the simulation is relatively easier than some of the earthquake problems that we dealt with. So because the system remains elastic, that helps you. The wind load can be predicted with high accuracy compared to earthquake load, for example. So we will have more information. In fact, we have a lot of information about wind, especially if you're going to put up wind farm at a given location. We can collect data pretty quickly, and there's historical information available. Loads on tower segments will be more realistic, which will improve the design and its dynamics compared to what we do today. So provide more accurate fatigue loads. So one of the big unknown in the wind world is the fatigue loads. If you talk to one company, they will say, oh, we expect them to, you to design for 5 million cycle fatigue load. Another company will say 10 million cycle. There's no consensus. It's a big, wide range. That's something that we can help them establish. Testing on segments and connections can be done separately with the hybrid technology. And we can certainly promote more cost-effective and safe design of tall wind turbine towers in the U.S. and around the world. So that's pretty much my last slide, just to tell you that I just wanted to share with you where this is going, what the potential is. I think the hybrid simulation can be very effective in helping an industry that industry doesn't know that they need or they would even can benefit. And this industry is very close network. It's hard to break in. It takes years of time to do it, but that's what we all are good at doing, right?